I spoke in a previous video about powers of complex numbers. How, for example, if I have a complex number w that is r e to the I theta, so it's got a modulus of r and an argument of theta, then its square, w squared, will have a modulus of r squared, we just square the modulus, and an argument of 2 theta. We double the argument. For w cubed, we would cube the modulus and triple the argument. And it keeps on clicking round with w cubed and w to the power 4, etc. But what about going backwards? What if I asked you for the square root of a complex number? Not only the square root, but the cube root, the fourth root, the fifth root. How do we root a complex number? We could think about just going backwards. So if I wanted the square root of w, instead of just thinking about that, let me be more specific. I want a complex number such that when we square it, it gives w. That makes the definition of square root here slightly more specific. Well, let's just do the opposite as what we did over here. Let's take the square root of the modulus, and that's okay to do because r is positive, and half the argument. So this would equal root r e to the I half theta. That there is a complex number that would square to give w. Let's show you that on Geogebra. I showed you this setup last time where I have a complex number z and I can raise it to certain powers and we can see where those powers are. So if I want a complex number z, and let's say I want to square it to give 2 plus 2i. So this complex number here, this blue one, squares to give 2 plus 2i. Let's play around with this a little bit. We've seen that when doing powers of complex numbers, it works in this spiral pattern because of how the modulus and argument works. And if I play with this a bit and move it around, in this spiral pattern, I can make it land on 2 plus 2i round about there as well. So there's another complex number down there that squares to give 2 plus 2i. Are there any others? Can we make it land on 2 plus 2i again? So that was our original one. That's too far away. That is... No, I'm fairly convinced that it's just those two. Which makes sense because we're solving a quadratic here. There's a squared in our little equation that we wrote down, and so it should just have 2 solutions. I'm going to show you how to find those 2 solutions on paper. Here we go. This is what we're doing. Find the solutions to z squared equals 2 plus 2i in the form a plus bi. I've already started this. I've done a sketch of the complex number that's given. That is useful when finding the modulus and argument of it, which is what we need to do first. So let's call this thing w. And we have that w has a modulus of this length here. Let's use a bit of Pythagoras in our heads. 2 squared add 2 squared is 4 add 4 is 8. So root 8. And its argument there, we've got a nice easy one. It's an isosceles triangle. So we've got this. Now using the technique that we did before, we can find z by taking the square root of the modulus, square root of a square root. I suppose I could write this as 8 to the power of a quarter, but let's leave it like that. So we've square rooted the modulus and we half the argument. There we go. That is the complex number that we found before that is down here somewhere. How do we find the other one? We go back to this original modulus and argument, and we use the fact that arguments repeat every 2 pi. Let me rephrase that. If we add 2 pi onto the argument, we get back to the same complex number. So if I add on 2 pi to this argument here, some fractions work in my head. 2 pi is the same as 8/4 pi. So this becomes 9/4 of pi. I've added on 2 pi to the argument, which means I've done a full loop, and these two complex numbers are exactly the same, which is why I've put an equals there. Now, if we do that method to these new ones, to this new way of writing it, the modulus is the same, but the argument, when we divide this argument by 2, is now different. We get 9 pi by 8. Now, those two numbers are not equal. These two original ones were equal because we just added on 2 pi, but in halving the argument, we've split them up. So put a comma in between them instead. We have these two complex numbers now as our solutions. This question asked for this form. So let's write these in a plus bi form, in the Cartesian form. And we can plug it into our calculator. Plug that into our calculator. So plug this bit into our calculator, this bit, and then do the same for that. I'm going to do that on my calculator now and get back to you. Great. There we are. And I've noticed that this second one is just the first one, but negative. It turns out to be exactly on the other side, down there. Let's just check those quickly in Geogebra again. So if I plug these in exactly, well, I say exactly, I rounded them both to 3 decimal places, 554 minus 0.644i, and press enter. Brill. And that is spot on to 3 decimal places. That squared becomes 2 plus 2i. Fantastic. I'm going to do one more example for you now with a higher power in it. So this technique is very similar for solving the higher powers. This question here has asked for answers just in this form, so we won't need to do that calculator bit in the end. But note, when it asks for this form, we need a range for the argument that we come out with at the end. Okay, starts out in the same way. We have this, which I'm going to call W. We find its modulus and argument. I'm going to do that on a calculator because they're slightly bigger numbers. We've got 16 squared plus 16 root 3 squared gives 32. Lovely. That length there is 32. And the argument is going to be the inverse tan of 16 root 3 over 16. Well, 16 root 3 over 16 is just root 3. Oh. pi by 3. Lovely, a very nice one. Now I'm going to write this in different ways by adding or subtracting 2 pi on each time. Whether I add or subtract 2 pi depends on the range for the solution that is given to me. If the range had been given between 0 and 2 pi, so just positive arguments, I would have added on 2 pi lots of times. I would do that. But because the solution set needs to be between negative pi and pi, I'm going to add on 2 pi a couple of times and subtract 2 pi a couple of times. I've just noticed a little mistake that I made, but I've noticed it because I've done a sketch. The inverse tan came out as pi over 3, but it's below the axis, so this one should have been negative pi over 3. Okay, let's subtract 2 pi a couple of times. So 2 pi is 6 pi by 3, so this becomes 7 pi by 3, and 13 pi by 3. Then I'm going to add 2 pi on the original thing. And add it on again. So I have 5 complex numbers. They're actually all the same complex number. I'm stopping at 5 because this should have exactly 5 solutions. Now, we'll do what we did before. We're going to find the 5th root of all of the moduluses. The 5th root of 32 is 2. And I'm going to divide the argument by 5 this time. And these new complex numbers are not all the same. So I'm going to write commas in between them instead. There we go. A last check here. Let's check that each of these arguments are within the range that we need. So these 3 are all bigger than negative pi, and these 2 are less than pi. Fantastic. So I'm happy with those 5 solutions. A last thing, where are those 5 solutions? We saw in the last one that these 2 were like reflected from each other. One was the negative version of the other. But where do all these 5 come out to be? I have a tool for that on Geogebra as well. This tool lets me put in a complex number and see where the roots are. So what we have is 16 minus 16 root 3 I, which is all the way down there. Let's zoom out just to check it's in the right place. 16 minus 16 root 3i, that looks about right. And the solutions that have come out are in this perfect pentagon there. I'm going to go more into, I'm going to dig a bit deeper into those shapes in a future video. Well done following along with that, and you should practice now by solving some more equations that look like that. Good luck.